Hi guys, and welcome to Chapter 3. I thought long and hard and actually recorded several other takes of this video before I decided to go with this. Usually I'm kind of reluctant about introducing a new unit using a video rather than in person, often because I do have activities and things that go along with it. However, I hate to lose the time, and since most of the stuff in the beginning of Chapter 3 is stuff that you've ostensibly learned in algebra classes, I'm going to assume that the most difficult part of this is not going to be the content so much as you're going to have to unlearn some of the stuff that you learned in algebra. And I'm not kidding about this. There's going to be stuff, especially with the calculator that you think you know, that's actually incorrect. So please try to pay attention, especially for those things. Now, because you guys have not actually picked up the notes, the examples packet for this chapter, you are going to need that in front of you. So either you might want to print out a copy of that, because I'm going to put the PDF on Blackboard, or you might want to just take notes on your own paper, which is fine. You'll just probably be pausing more often to write things down. You're also going to need your formula sheet, or the back of your textbook if you've happened to lost yours and have not printed out a new one. And you're also going to need your graphing calculator. So go ahead, if you need to go and grab those, either print out or paper to take notes on, your formula sheet and your graphing calculator. Pause the video now, and I'll see you when you get back. So this is the beginning of chapters 3 and 12, which I put together in one unit. And it's really about the relationship between two quantitative variables. Now, we just got done with doing this in chapter 11, when we talked about the chi-square test for association or the chi-square test for independence. And that's checking to see if there's a relationship between two categorical variables. Chapters 3 and 12 is still bivariate data, but it's about, is there a relationship between two quantitative variables? So just to get us started, this first example here is talking about the explanatory and response variables for a pair of variables. So here are two variables, the amount of rain and the amount of weed growth. So for these, most of you guys would probably say that the amount of rain is probably going to be the explanatory variable, and the amount of weed growth is going to be the response variable. So as the amount of rain changes, the amount of weed growth is going to change in a predictable way. The next one is probably not so clear-cut, the winning percentage of a basketball team versus attendance at games. And most of you guys will probably immediately think one way or the other. To be honest, you can probably argue this one either way. So if a team tends to win more, then the attendance at games tends to also increase. But you might also be thinking that as your attendance at games increases, there's more support, there's more fans, then the basketball team may also tend to win more games. I'm not going to weigh in on this one. You probably have one that you think is more likely than the other, which is fine, but this is an example of one where it might not be so clear-cut, and you could probably argue it either way. The third one, resting pulse rate versus the amount of daily exercise. So for this one, most of you guys would probably agree that the amount of daily exercise is going to be the explanatory variable, and the resting pulse rate is going to be the response variable. So it's not always clear-cut. Like I said, for B, it's not clear-cut which one is which. For A, as the amount of rain increases, your weed growth would probably tend to also increase. For C, as your amount of daily exercise increases, your resting pulse rate would probably tend to decrease. So even if there is a relationship between two variables, it could be a positive one, meaning as one increases, the other one also increases, or a negative one. As one increases, the other one tends to decrease. In the box, I put a couple pairs of variables. Go ahead and pause the video and see if you can figure out for each of these which one you would consider the explanatory and which one you would consider the response. And I'll see you when you get back. All right, so for this first one, looking at students' test anxiety and their performance on a standardized test, most of you guys probably thought that test anxiety was the explanatory variable, and the performance on a standardized test would be the response variable. It's better if you can word these so that it's clear that these are quantitative variables. So if you said something like level of test anxiety or something like that would probably be even better. Performance on a standardized test, like a score on a standardized test or something like that, would probably be even better. For the second one, looking at the volume of the hippocampus, which is an area of the brain, and a short verbal retention assessment. Most of you guys probably thought the volume of the hippocampus was going to be the explanatory variable, and the performance on a short verbal retention assessment would have been the response variable. Now we're going over these for a couple of reasons. First of all, there's not always going to be a clear explanatory response variable relationship between two variables taken on a single subject, or individual, depending on if you're using people or not. Second of all, if there is, get used to figuring out which one is which, because it does make a difference when we start doing scatter plots. Now, this is something that I know is on the algebra curriculum and you guys have done before. It's one of the most common ways of displaying data, and it's the only way really to display relationships between two quantitative variables, which is kind of the point of chapters 3 and 12. So just to refresh your memory before we go to the next page, because I'm going to have you guys do that scatter plot by hand for real. The values you use on a scatter plot is bivariate. So again, one group, two variables, just like chi-square association or independence. It's just that these are now not categorical variables, but quantitative variables. And we put the values of one variable on the horizontal axis and the values of the other variable on your vertical axis. Each individual in your data is going to be a point on your graph. So each of these points, the x-coordinate is going to be the value for one variable, and the y-coordinate is going to be the value for the other. Just as a reminder, before you turn the page and start making a scatter plot, first things first, figure out which variable should go on which axis. If there's not a clear explanatory response relationship, it doesn't really matter. But if there is, then your explanatory variable should be the one that goes on your x-axis, and your response variable should be the one that goes on your y-axis. If you've taken this sort of thing in other classes, you might have heard these referred to as independent and dependent variables. In algebra, that's often what we call them. In other fields like psychology, it's what you call them. In statistics, the words independent and dependent have specific meaning. Independent means that knowing one value of a variable doesn't tell you anything about the other possible values. So we don't use those words in the same context. So we tend to say explanatory and response. Labeling and scaling your axes. I cannot emphasize this enough. This is really, really, really important. On the actual AP exam, you do not have a ruler. You are actually not permitted to bring rulers into the exam with you. So it's not such a big deal that like your scaling is perfect or your lines are perfectly straight, because we don't expect them to be. I mean, obviously you don't have rulers. But remember, it's all about context, it's all about communication. Labeling. Always, always, always label your axes. This is the number one, least reasonable thing that you can do to lose points. I mean, come on, you don't want to lose points because you forgot to label your axes. Scaling your axes. While it's true that a lot of the time when we look at quantitative data, in the real world they only have real world meaning if they are positive numbers, and that means a lot of times we're working in the first quadrant where both values of the variable, where the values of both variables have positive values. That doesn't necessarily mean you have to start at 0. Just use a consistent scale that makes sense. It doesn't have to include the point 0. Also, of course, if it's something that does have a negative real-world meaning like temperature, then yeah, it may not even include the point 0 because you're dealing with only numbers that are negative or numbers that are both positive and negative. And you're going to do that before you plot your individual data values. Okay, at this point, you should pause the video, go ahead and do the example on the next page by hand. This is probably the only one where I'm really going to ask you to do it by hand, and then come back and then we'll see how you did.